So we know that this particular fairly typical quasar has a luminosity of 3.4 by 10 to the 40 watts. Now that's an inconceivably large number. In this video I'd like to try and put it in perspective by working out what effect something with that luminosity would have on us if we were nearby. So let's imagine our quasar, whatever it is, we'll come back to what it is over here, and that we are floating in space some distance away. And let's say that distance is 40 astronomical units, which is the distance from the Earth to Pluto, from the Sun to Pluto. So we're as far from the quasar as Pluto is from our Sun. We know from our own solar system that Pluto is a very cold, dark place. What would it be like if you were this far from a quasar? Well, we can calculate how much radiation hits a person. So you've got a person, they're about, say 2 meters tall, maybe about half a meter wide. So their surface area of a person is about 1 square meter. So we've got a luminosity here, the flux there. So the energy absorbed by a person is just going to be the flux times the area, and the area is 1 square meter. So we know that flux equals luminosity over 4 pi d squared. We don't need to worry about redshift 1 plus redshift here because the universe isn't expanding appreciably over this short distance, which comes out as 3.4 by 10 to the 40 over 4 pi, 40 astronomical units, 40 times 1 astronomical unit, which is 1.5 by 10 to the 11 meters squared, and that comes out at 7.5 by 10 to the 13 watts per meter squared. And as the person's got about 1 square meter, that means the power absorbed by a person is about 7.5 by 10 to the 13 watts. Sounds like a lot. Is it a lot? Well, we can compare it to something. The atom bomb that hit Hiroshima was a 12 kiloton bomb, which meant it had a total energy output of 5 by 10 to the 13 joules. So what that means is if you were sitting out at Pluto's orbit around one of these quasars, the amount of energy that you'd be absorbing every second is more than the total energy from the Hiroshima atom bomb. And of course, an atom bomb, not all the energy is focused on one person, it goes in all directions, but just imagine all the energy from the bomb hits you, doesn't go any other direction. You'll be getting more than one of those every second. So that's giving you some idea of just what this incredible luminosity means. It's absolutely incredible. This is really bad sunburn, if you like, an atom bomb per second on your surface. That's what it would do to a person. It wouldn't be pretty. What would it do to the Earth? Well, let's imagine we've got this same radiation hitting the Earth. We can, for example, work out what it will do to the oceans. We've got the oceans covering some fraction of the Earth. So what's the surface area of the oceans? Well, the surface area of the whole Earth is 4 pi r squared. It's r of the Earth squared. Now the oceans cover 2/3 of the Earth's surface, so multiply by 2/3, and at any given time only half of them are going to be hit because the other half is going to be in night. So times a half. That gives you an estimate of the area of the oceans on the Earth, which comes out as about 1.7 by 10 to the 14 square meters. So how much energy is arriving? So the energy input per second is equal to the area times the flux. We've got the area, we've got the flux, and that comes out as about 10 to the 28 watts. Another meaninglessly big number. 10 to the 28 is far too big for any human to know what it really means. Would that heat up the ocean? Well, we can estimate that. What's the total mass of the world's oceans? On average, they're about 4 kilometers deep. So the volume is just equal to the area, which we've already worked out, times the depth, which is 4 kilometers. The mass is equal to the volume times the density. Density of water is 1,000 kilograms per cubic meter. So the mass is the area, 1.7 by 10 to the 14 meters squared, times the depth, 4,000 meters roughly. Of course, some bits of the ocean are deeper, some are shallower, but that's a reasonable average, times the density, which comes out as about 7 by 10 to the 20 kilograms. So if you compare these two numbers, you can see we're getting about 10 to the 7 watts per kilogram of ocean. So 10 million joules of energy every second to every kilogram. So how much will that warm the ocean up? Now we know that to increase the temperature by an amount delta T of something, the power needed, so the energy needed, is equal to the mass times delta T times the specific heat capacity of whatever it is you're warming up. So in this case, for water, that's 4,200 joules per kilogram per degree. So how long will it take to warm the world's oceans up by 1 degree? So if delta T is 1 degrees centigrade or Kelvin, we need an energy of, say, for 1 kilogram times 1 degree C times 4,200. So we need 4,200 joules. How long does that take? So the time is equal to the amount of energy required divided by the power. Which comes out at about 0.4 microseconds. 0.4 by 10 to the minus 6 seconds. So the world's oceans are going to heat up very, very fast. How long to bring them up to 100 degrees? In that case, we need to change it by 80 degrees, because the average ocean temperature is about roughly 20 degrees. So multiply that times 80, gives you about 0.03 seconds. So 0.03 seconds, faster than you can blink, a quasar will bring all the world's oceans up to 100 degrees. It then has to boil them. To boil something, you need to use the latent heat. Latent heat of vaporization of water is 2 to 60 kilojoules per kilogram. That's how much energy you need to put into water at 100 degrees centigrade turned into steam at 100 degrees centigrade. So you can work out how long it takes to produce that. So the time, once again, will be the energy we need, 2260, that's kilojoules, so times 1,000 joules, divided by the power. Remember, power is energy per unit time. So we've got energy divided by energy per unit time, so that gives us something with the time, so 10 to the 7, which comes out at about 0.2 seconds. So what have we learned? Quasars are very, very powerful. They boil the world's oceans at least the half of the oceans that are facing towards them, in a fifth of a second. And that's if the Earth was out at Pluto's distance away from it. Very, very powerful.